faculty and staff, and especially our students, many of whom you see here today. Welcome to Forsyth Tech. It's really a pleasure and honor to be here today and be a part of what's a very important community partnership and community collaboration that we're celebrating today. The purpose of our event today is to really introduce and unveil the prototype of a new training device that has been developed, invented by Dr. Joshua Nitsky. It's been developed by Wake Forest Innovation, and then has been designed and built by Forsyth Tech and Forsyth Tech students. The prototype has been. And this is a tremendous example of how Winston-Salem and this region is coming together in collaborative efforts to build the economy, to create new opportunities for people, and to create new science and new innovation to better the lives of our community and to better the lives of many people throughout the world through innovation such as this. This kind of collaboration is very important to us, certainly as a college. I know it's important to Wake Forest Innovation, and you're going to be hearing from folks from Wake Forest Innovation as well. But following some introductory remarks, and Dr. Nitsky will be demonstrating the device, and we'll be taking questions and explaining much better than any of the rest of us can the value that we see in this collaboration and the resulting product of it. I want to thank John Castle, who is the director of our sonography program here at Forsyth Tech, for the use of our lab this afternoon. John, thank you very much. I have a number of people from Forsyth Tech here. I want to introduce you all, but thank you, John, for that. With that, I'd like to introduce the executive director of the president of Wake Forest Innovation, the president of Wake Forest Innovation, Eric Tomlinson.
Thank you.
Eric, welcome to Forsyth Tech.
Thank you very much,
Yeah.
Gary. Thank you. It's my pleasure. It's my pleasure to be here also with my colleagues from Wake Forest Innovations. I am between you and the demonstration of the model, so I'll be very brief. I'd like to thank everybody involved in the conception, the design, the actual prototyping, and the creation of this brand new device. It's not without anybody's notice that this city is changing rapidly. It's becoming truly a city where innovation and innovations take place, and certainly Forsyth Tech Community College is at the vanguard of that new development in our city. So we're delighted to have partnered with the students and the faculty to help our proud inventor here, Joshua Nitsky, who is an assistant professor at Wake Forest Baptist Medical Center in developing this product. So, Joshua,
thanks.
Over to you.
All right. Welcome. Good afternoon, everyone. So as Dr. Tomlinson mentioned, my name is Josh Nitsky, and I am what's in doctor's terms called a maternal fetal medicine specialist. So in plainer language, I'm a high-risk pregnancy doctor. So some of the women I care for require invasive procedures, such as an amniocentesis to perform genetic testing on, or perhaps their baby would need an intrauterine transfusion because it's anemic. And these procedures are things that are done generally under ultrasound guidance. And unfortunately, the current training in these procedures is the classic see one, do one, teach one paradigm. So as part of my role at Wake Forest, I play a large part in the education of OBGYN residents and maternal fetal medicine fellows and training them to do these sort of procedures. And the see one, do one, teach one approach generally leads to a lot of training anxiety. So coming up with a, say, for lack of a better word, a safer environment for the students or the trainees to perform these procedures is kind of what I was thinking of when this kind of invention came to mind. So my former fellowship director, Dr. Brian Brost, and I came up with kind of a basement workshop sort of version of this trainer and constructed some what we call targeting tasks that helps a trainee kind of improve the global hand-eye coordination that they'll need to safely and successfully perform these procedures in real life. So by using this device, they can, literally practice hundreds of times before they have to do their first real life procedure. And I think that's kind of better for everybody involved. So the way this trainer kind of is constructed, this is really nothing more than a water-filled bucket into which several little targeting, what I call targeting constructs, are placed. These are just two examples of the one. I have several others as well. And that's placed at the bottom of this bucket with a magnet so it doesn't float away in the water. And then the chamber is covered with some sort of simulated skin. In the case of this, this prototype here, this is ballistic gelatin, the sort of thing they use in CSI to fire guns into and do the ballistics on it. That's why it's called that. And this is a more upgraded version of a silicone skin that's a little more durable, a little more realistic looking, and that sort of thing. So, in addition to allowing folks to practice the procedures, one of the other issues that comes up with these sort of procedures is there's not a very objective way to assess a trainee's skill or competence in a procedure. They're generally very complicated and multi-step procedures that have to be done, so it's hard to come up with a checklist or a grade of 1 to 100 on how they did. So it's difficult to know when someone's ready, so to speak, to perform these procedures. With these tasks, the thought behind these was partially to address that as well. Is, say, in this task, the trainee would have to put a needle in the different straws in a random order, and you can time them how long it takes them to do that, and also record the number of times they make mistakes. And you can come up with a more objective, say, score, number, or something, and come up with benchmarks that they have to, exceed in order to perform procedures in real life. And you can also, track one's progress over. Maternal fetal medicine is a 3-year fellowship, so they can be tracked over time to see if they're kind of meeting the marks that they need to, and if not, they can get remediation, or if they're really excelling and doing well, they can be set free from supervision and allowed, the graduated responsibility that is common to many medical training programs. We've actually used this prototype, my collaborator, Dr. Brost, and I, at this year's annual meeting of the Society for Maternal Fetal Medicine. We held a half-day workshop on ultrasound-guided invasive procedures, the ones that are specific to our field, like amniocentesis and similar, and they were very well received by all of the participants. And in fact, we got several requests to take the show on the road, so to speak, and bring it to different training programs throughout the country. We have one visit already set up for this coming November at Madigan Army Medical Center in Washington State. And we're going to be doing a whole day's course there with maternal fetal medicine fellows at Madigan and those at the University of Washington in Seattle as well. So we're very excited about that, to get more feedback and refine the things further. I've actually just last month, I took it on the road down 40 to Duke and Chapel Hill. Both of those medical centers have maternal fetal medicine fellowships. So I was able to run the faculty and the fellows through these tasks and get their feedback and see what they thought. And again, we got all very positive things. And I'm trying to organize what I term a fellow boot camp, where the fellows from our institution, Duke, UNC, and actually even the Medical University of South Carolina would come to Winston-Salem and go through a more intensive course at the beginning of the academic year to kind of prepare them for their future careers. So what we're hoping for is the next steps would be, although the targeting tests I've come up with have been more engineered towards amniocentesis and the other procedures I perform in my particular practice, ultrasound-guided invasive procedures are performed in any number of specialties: radiology, critical care, anesthesia, just to name a few. So I think it would have value beyond just my field, and that it can be very useful for all numbers of trainees in a variety of medical fields. So one of our hopes is to kind of move it to other specialties outside of obstetrics and maternal fetal medicine. And one other modification we're hoping to add soon is some electronic performance tracking. So there's software and sensors available that you can, in real time, record kind of the path that a needle takes from the, say, the simulated skin to the target, and you can calculate an optimal path and then quantify the amount of wiggle that a trainee or even experienced provider has going from point A to point B. And that would be another even more objective way to assess someone's skill and get a, track performance in a better way to hopefully, increase the safety and success of these procedures when they're performed in real life. So it's been a real pleasure working with the folks here at Forsyth Tech, the students in particular. It's been, totally outside of my experience talking about the difference between silicone and ballistic gelatin and this sort of plastic versus that sort of plastic and what can and can't be done. So that's been very informative and a real joy for me. So I'd like to thank David Dinkins and the folks students at Forsyth Tech. Unfortunately, there are quite a little too many of them for me to name one at a time here. So now I'll kind of stop it there and allow Ken Russell, the Director of Product Innovation Services at Wake Forest Innovations, to tell more about Wake Forest Innovations' role in developing our trainer.
Thank you. Thank you, Don.
You're welcome.
I'm Ken Russell, and good to have you here this afternoon. Glad to be here. As Director of the Medical Device Development Program, we work with our faculty and staff all across the Wake Forest Baptist Medical Center who have ideas for developing medical devices. And medical device ideas get commercialized with us, and as we do that, they go through several design phases. And the design phase, this one went through with Dr. Nietzsche to start with, was he took it from an idea to an invention. He took it out of his head, put it on paper, he then prototyped it, did some proof of concepts and some validation testing, and that's when he contacted Wake Forest Innovations. He said, okay, I got it this far, what do we need to do now? Well, we protected it, it's patent pending technology, which is wonderful, and then we looked for the next phase of design, which was to take it from an invention to a repeatable manufacturable product. And that's what you have here at Forsyth Tech. That's what we needed, okay? You take this invention and you do very good dimensional drawings with tolerances, solid models, manufacturing notes, and so forth to make this repeatable. So we got that done through David Dinkins' class, the Mechanical Engineering Technology class, and we got the manufacturing done through the Advanced Machining Technology program, Advanced Manufacturing Technology that Todd Bishop has set up. And we got these wonderful devices, and you just heard of the success that he's having showing these around. And we're very proud of this and very proud to be here with this. The last thing I'll say before I turn over to my colleague Muhammad Alba is very simply this. The tools that Forsyth Tech has here, the CAD systems, they're equivalent to any medical device company I've ever worked with. The machinery that you see here, that they made these on, it's the same thing if you went out and toured Honda Jet at the airport, okay? The bottom line is, you can make anything. You can make anything here. Medical devices, whatever you want, you can make it. You have the manufacturing and the design capability to do it. And that's wonderful for us. It's a wonderful partnership, and we really appreciate it. Thank you.
Yeah, thank you, Ken. I just want to talk about the experience that actually I had with the students. I was actually involved in working directly with the students and Todd and David Dinkins, and really participate in co-mentoring the students throughout the project. So really I had a lot of interaction with Joshua and James really almost on weekly or monthly basis to follow up on the design, on the prototyping and the process overall, and be in direct contact with Dr. Nietzsche to update him with the progress and get a feedback to the students. And really we work on real life problems with the students where they actually coming from an industry, really you have to deal with the inventor and to get a feedback on the design. So this is actually what we provided the students with, to work directly with the inventor and get a feedback and work based on his recommendation. So it was really a nice experience. The students, they went above and beyond, and we had a deadline that we did not miss, actually. We delivered the prototypes a few days before the targeted deadline, and Dr. Nietzsche was able to try them before he goes to the annual meeting. So really it was a nice experience to be in a city like Winston-Salem, where we can really apply our leadership vision for an open innovation. Open innovation for us means that we can work with anybody who has the expertise and capabilities to accelerate the journey from discovery into a commercial product. So really we were lucky to be in Winston here, within a close proximity to Forsyth Tech, where not only the quality of the education is really phenomenal, also the students, the professionalism, the time. Really, we started working on this, and in just no time, really, we got it done, and we are happy with the progress. So again, I thank the students, David, Todd, for really what they allowed us, and I'm looking forward actually to more projects to work on with Forsyth Tech. Thank you. And now I'll let David talk about Forsyth Tech stuff.
Thanks, Mohammed. My name is David Dinkins. I'm an instructor in mechanical engineering technology. And I did want to say that we really appreciate the opportunity to collaborate with Wake Forest Innovations on this project. This was a perfect project because obviously it was a great idea. They had the original working prototype proof of concept down. And as Ken stated, they just needed to take it into more of a manufacturing environment and optimize the design to make it feasible for mass manufacture and to make it cost effective as well. So the experience has been great, and the students have really enjoyed it because it's given them an opportunity to work on a project outside of the normal classroom environment where we're just doing simple case studies and classroom assignments, but go above and beyond and do an actual real-world working prototype, especially something that improves the lives and health of people. So I commend these guys. They've done a great job. Our mechanical engineering technology students, as well as our computer integrated machining students. We were able to take it from the design side all the way to the actual production so that we had a physical working prototype. So my hat's off to you guys. You really did some great work, and they spent a lot of time even outside of normal classroom hours to make this happen. So I just want to give a special thanks to them, and also for the leadership of Todd Bishop, who's our department chair of engineering technologies. So I'll turn it back over to Dr. Nietzsche, who will actually demonstrate the device.
All right, gotta roll up my sleeves here, so to speak, and literally figure. And this water-filled chamber is one of these. So a series of straws that, you know, say could represent an artery or a vein just about anywhere in the body, and ultrasound is used to guide needles, various devices into them at all different locations. The one that comes up in maternal fetal medicine is that sometimes babies need a transfusion inside the uterus, and I have to put a needle in the umbilical vein. So this is just some ultrasound gel. It's on top of our synthetic skin, which in this one is ballistic gelatin. And you can kind of see there, you can kind of picture a straw or a vessel there. So that view that you see there is the equivalent of me scanning kind of right like this over the middle two straws. And so the task that kind of goes with this one is the person has to insert the needle in the different number straws in a random order in under 3 minutes. And they can't miss, well, if they miss, they get a penalty assessed. So say, for example, if I were going to try to put the needle in the straw closest to the right of the screen, I'll insert my needle here and guide it into the straw. And then say if I was going to guide the needle into the straw, this is the straw that's closest, furthest to the right of the construct. I would take a slightly different angle based on how it's oriented. And put the needle in that one. So they, you know, go through 10 or so different straws to put it in and refine their technique. well, I'm not bragging or anything, but my path is smoother than, say, the residents or fellows would be. So, you know, for example, a lot of people would do, say, something like this, and then the needle would disappear and go back and forth. And the needle disappearing is obviously not desired because you want to know where your tip is and you don't put it in the wrong place. So you kind of want to, the reason that ultrasound guidance increases the safety is you know where your device is at all times. And they might, you know, overshoot a little bit or something like this, which would be a penalty. So over time, my hope is that they get pretty smooth and kind of go straight into the various straws. We have a couple other tasks. I pointed out this one before. If you ultrasound it kind of in this way, it appears as very bright little circles when you get a cross-sectional view of the little rods here. And you can practice touching the rods in various random orders. So you would practice adjusting your needle path. So for example, like if I was going to insert into this straw, right, I would have to change my needle path this way to get into the other straw. So that rod model is designed to help folks adjust the needle within the same ultrasound plane. In OB, that's kind of most important in that when you do an amniocentesis and you have a little fluid pocket lined up, babies sometimes don't cooperate and move into the pocket that you were going to put the needle into, and now you have a different pocket that's at a slightly different location, so you have to adjust as you go. Or, you know, mom moves unexpectedly or something like that, and now things are not in the same configuration as before. So being able to adjust kind of as the procedure unfolds is a very valuable skill to have, and this allows folks to kind of do that. And I have my basement water bucket version of this, a couple of them in one of the ultrasound rooms at one of our offices, and the fellows and residents can just fill them up and use them, you know, at off hours, and they know the tasks to do. So it's nice for me to be there so I can critique them and give them guidance, but they can also practice without the faculty around, which is a nice advantage to have, because in many cases faculty time can be the limiting factor in training, you know, medical trainees and various things, which I'm sure you all are aware of over here to my right. So I'm happy to entertain questions, demonstrate different things, but that's kind of the gist of it, in that although these are conceived with maternal fetal medicine and obstetrics in mind, it's very easy to think of another construct or another modification that would make this, you know, more useful for other fields. For example, a thoracentesis, or drainage of fluid from the chest, is often done under ultrasound guidance. It'd be very easy to pour one of these ballistic gels with rods or various things to simulate ribs, so that you could, you know, ultrasound between ribs and insert needles and catheters as they do for those procedures. Many procedures also require somewhat complicated deployment steps for various devices. Say if you're going to put a central line or a catheter in someone's external jugular vein, there's various steps where you put guide wire in, followed by a bunch of other devices. So you can practice those serial deployment steps that are, from experience I can tell you, are not very intuitive and sometimes the much harder part of the procedure. So you can practice doing all the deployment in addition to guiding the needle to the appropriate target. So.
Thank you. On behalf of Forsyth Tech, I want to say thank you for being here. I'm Mamie Sutphin, and like Dr. Nietzsche said, we'll open the floor up for questions. I do want to add, if I can, a personal note. I have a 3-month-old at home. I think it's appropriate to say, fortunately, Dr. Nietzsche was not my doctor. But on behalf of mothers and children and what you're doing here, you know, the patients who will be the benefactors, what you've done, what our students here at Forsyth Tech have done, this is remarkable work. It really is, and we want to celebrate that and say thank you so very much.
Oh, my pleasure.
Thank you. This time we'll open it up to the media for your questions. If you want to do individual interviews as well, we also have a room next door where we can do some of those also. But we'll go ahead and open up for questions now.